Hello everyone, in this video we'll be studying the design of eccentrically loaded bolted joints. So here you can three figures are showing the different types of eccentrically loaded bolted joints. In this video we'll be discussing mainly the first type. So in this first type you can see, or it is named as the load acting in the plane containing the bolt. So here you can see a plate onto which this plate is joined with the help of this bolts, and its CG of this bolt sections will be coming here, and the load is also acting in the same plane that is containing the bolt, and it is not acting through the CG, so it is separated by distance, and this distance will be known as eccentricity. So this makes it a eccentrically loaded bolted joint. And here you can see the two views of this joints are shown. So here the bolt axis is actually coming, and this bracket is coming in this direction. So here load is acting here, so load is actually not in the plane, but the load is in a direction perpendicular to the axis of bolt. So this is the type 2 eccentrically loaded bolted joints. And in the last case, the bolt axis are coming in this direction, and load is acting in a direction parallel to the axis of this bolt. So this is the case 3. And in this video we'll be discussing the detailed design of this bolted joint or bolt which are coming as a part of this type 1, that is load. The eccentric load is acting in the plane that is containing the bolts. So let's get into it. So here you can see this three figures. First we'll be starting from the leftmost one. So this is showing you the two plates joined by this bolted joints. So here you can see 4 bolts which are coming in this plane, and first step will be to obtain the CG of this bolted joint. So here 4 bolts are there, you can consider it as a point, and the CG of this locations, if you are having a coordinate system, and if you are naming the bolt as 1, 2, 3, 4, then this will be having, if this is the 0, if you are having some coordinate system, then you can suppose this coordinate system is lying here. So this is the x coordinate and y axis. Then you can find the CG by x1 plus x2 plus x3 plus x4 divided by 4, since you are considering the bolt locations as points. And similarly the y coordinates of CGS y1 plus y2 plus y3 plus y4 divided by 4. So if you are solving this one, then you will be getting CG. Otherwise also you can based on this symmetry or observation, you can obtain that CG will be lying here. And next you will be evaluating the distance between this CG up to the position where load is acting, and that distance will be known as eccentricity. So next step will be to transfer this eccentric load acting at this position to this CG. For that we will be considering an equal and opposite forces, and out of these two forces finally we will be placing this force as such here. So F will be remaining there, and these two, or this pair of forces, that is F acting upward and F acting downward, will be creating a clockwise moment, and this will be creating a clockwise moment, and the value of that moment is equal to F into the distance between this one, that is F into E. So as a result, in the final loading diagram we are having a load of magnitude F acting along the CG of this bolted joints, and a moment, it is actually a torsional moment, then value is F into E. So now we will be seeing the effect of this load, or what is the effect of this load F and Fe on this bolted joint, and based on that we will be doing the design. So first here we will be taking the effect of load. For that I am drawing these bolted joints. The bolted locations are shown, and here I am marking only the external force that is acting F. And if you are observing, bolt are lying in this plane, and in a direction parallel to this bolt the load is acting. That means the load is tangential to this bolt cross section. So this will be creating a tangential stress which is known as shear stress, and that shear stress will be known as primary shear stress. So this shear stress will be calling as the primary shear stress, or will be first evaluating the load. So this will be creating the primary load. Since all bolts are of same cross section, the contribution or the load share taken by each bolt will be same, and I am naming it as F1A, F1B, F1C, F1D for all of these bolt locations. And if you are seeing, since it is same, so F1A will be equal to F1B equal to F1C equal to F1D, and that will be equal to the total tangential force divided by number of bolts. Since 4 bolts are there, it will be equal to F by 4. I will be showing all the equations required at the end, which is given in the data book. This is given in this equation to find this. This is known as primary shear load. This is known as the primary shear load acting on each of this bolt location. So this is actually the primary shear load. And next, so this is produced because of the effect of load. Next we will be considering the effect of the moment F into E. So in this one you can see the effect of couple or moment F into E. If you are observing, this will be acting as a torsional moment because this will be trying to twist this or induce shear stress. So this will be considered as a torsional load, so torsional shear load, and that is known as secondary shear load, and I will be calling it as F2. So we have to consider or find the magnitudes of this secondary shear load at all of these locations, and the secondary shear load at A will be called as F2A, similarly at B F2B. So you are having F2C and F2D, and we have to calculate the magnitude of this F2A, F2B, F2C and F2D, and this will be fine in such a way that the moment created or the moment present initially is F into E. So now you are replacing this F into E to find and then you will be having the secondary shear load. So the sum of the moments of all these forces about CG should be same as this F into E. That means the moment created by F2A and the secondary shear loads directions will be coming in such a way that if you are having CG here and bolt location A here, then you can draw a line that will be giving you the shortest distance, and the distance will be known as RA. You can evaluate based on this geometry, and that will be discussed when we are solving a problem. Then F2A will be perpendicular to this line joining this bolt location and this CG. Similar, and in this direction it will be coming because the moment is clockwise. Similarly, F2B will be obtained, so line joining RB and perpendicular to this one and in this direction because it is clockwise. So in similar way you can draw the direction of F2C and F2D, and finally the moment created by F2A about the CG will be F2A into RA. Similarly the moment created by F2B will be F2B into RB. So you can write the initial moment present, that is F into E, can be replaced by the secondary shear forces, that is F2A into RA plus the next words F2B into RB. So finally you can have this expression for this F into E can be written in this form. And if you are observing, the secondary shear loads will be proportional to generally the distance from its CG. That means R is the distance measured from CG to the bolt location. It is the general expression. Then you can write F2A is proportional to RA and F2B is proportional to RB. In similar way you can write for all the bolt locations, and you can remove this proportionality sign by some constant. That means you can write this F2A as some constant K into RA. Similarly you can write the F2B as K into RB, and next term you can write like K into RC, and last time as K into RD. So you can substitute this terms here. So this will be written in terms of K into RA, and this will be K into RB, and this F2C will be K into RC, and this F2D will be K into RD. So if you are simplifying this one, then you will be getting the expression for K, which is equal to F into E divided by the RA square plus RB square plus RC square plus RD square. So if you are having the value of this K, then you can find the secondary shear force on F2A as this is equal to K into RA. So F2A can be written as K is actually F into E into RA divided by this sigma R square. I will be writing the RA square plus RB square plus RC square plus RD square. I will be writing sigma R square. In a similar way you can evaluate the secondary shear load at a B also, that is F2B. Don't worry, even if you are not understanding this one, I will be showing all the equations required in the data book. And you can write F2B as F into E into RB divided by sigma R square, and F2C as F into E into RC divided by sigma R square, where sigma R square is RA square plus RB square plus RC square plus RD square. So in this way you can find all the secondary shear loads at all of this bolt location. So now you are having this primary shear load created due to the direct force F, and the secondary shear load created due to the torsional moment or couple F into E. So from this we will be evaluating the net load which is acting on the bolt locations. So here we will be finding the resultant load acting on the bolt. So in bolt A we are already having the primary shear loads F1A, F2A, F3A, which are having equal magnitudes at all position and its directions are shown. And also the secondary shear loads at each of these locations will be same, because RA, RB, RC, RD are same, and we have obtained the expression, and its direction is in a direction perpendicular to the line connecting CG to the respective bolt location. So we are having the primary and secondary shear components. From this we have to obtain the resultant shear load. So at the bolt location A, I will be showing you how to obtain this the resultant of this primary F1A and secondary F2A. For that we will be using the parallelogram law. So first we are having the secondary component vector here, and that I will be placing at the end of this vector. So now you will be having this component here, and next I will be placing this primary component or the primary shear load at the end of this vector. So now you will be completing a parallelogram. And finally the resultant load acting on at this bolt location will be given by this resultant of this parallelogram or the diagonal of this parallelogram. That means this will be giving you the resultant load, and you will be calling this as FA. So this FA is representing the resultant load which is acting at this bolt location. And if you are having primary and secondary, and then you can evaluate the resultant shear load acting at this A by the F1A square plus, this is actually parallelogram law, and F2A square plus 2 F1A F2A into cos theta A. All these terms are coming under this square root. And where theta A is actually the angle between this primary and secondary. So this theta A you can evaluate, and for that you can use this direction, because this green vector F1A is perpendicular to this one and this one is perpendicular to this one. So angle between these two vectors will be same as angle between its perpendiculars. So you can find the angle theta A from here, and based on which you can evaluate FA. So in a similar way you can evaluate the resultant shear stress at all resultant shear loads at all of this bolt location that I will be showing you now. So in a similar way to the previous one, if you are constructing the parallelograms, then you can obtain the resultant shear load at all of these locations. So that is shown by FA, FB, FC and FD. And if you are observing, the resultant shear load at A and B will be same, and that will be the maximum for this case. That is FA and FB will be the maximum and the same. Similarly, FD and FC, as their vector length are shorter, this FD and FB will be minimum, and this FD will be equal to FC. So whenever we are designing, we will be taking the maximum shear loads which are acting on the bolt. And here you can see the maximum shear load is acting on the bolt A or B. So this same can be used for design. So we will be proceeding the design with this by taking this maximum shear load, and from that we will be evaluating the maximum. So this FA and FB are the maximum or resultant shear load. So this will be used for design, and from this you can evaluate the tau max, that is equal to FA divided by AT, where AT is the weakest section, that is the area, tensile area across the weakest section, and this will be equated to the allowable shear strength of the material that may be given in the question. So based on from this one you can find the value of this tensile area, and by looking onto the respective column in the or the table in the isometric thread, you can select the isometric thread having the minimum tensile area. So based on this one you can select the suitable bolt and you can specify that essence. So this is the design procedure for bolted joints which are subjected to eccentric load, which are contained in a plane acting that is containing the bolt. So we will be solving a simple problem here itself based on this one. And before that I will be showing you all the respective equations for finding this primary, secondary and this resultant shear load. So all these diagrams as well as equations are given here. So F by N is the way to find the primary shear load F1 and or the direct shear load, and this equation is giving you this how to obtain this secondary shear load, that we have already seen F into E into R divided by sigma R square I have shown, and this is similar expression F into E into C divided by sigma C square, and this will be becoming maximum when this distance C is becoming maximum. So here all these are symmetric, so here you can say take any of this R as the maximum secondary shear load. Once you are having the primary and secondary shear load, then you will be evaluating this resultant load using this expression. And if you are finding the resultant shear load at this position or this position will be coming for this bolt arrangements, and that theta you can evaluate from this will be the theta that is happening between these locations. So here we have to determine the size of the bolt which is loaded as shown in figure. So we have already discussed a case similar to this one. So first step will be to locate the CG and find the eccentricity. So here the bolt, this distance is 100 mm, so CG will be coming at along the mid of this line, and also this distance is 150 mm, so CG will be coming along this line. So if you are observing, the CG distance up to this point will be equal to 200 by 2, that is 100. Then you are having a distance of 100 mm again, and finally you are having the distance of 300. So if you are adding all these distances, then you will be getting the value of eccentricity, and value of eccentricity will be equal to 500 mm. So now you are obtained the eccentricity, and now we will be transferring this load acting at this the eccentric point to this CG. Then you will be having a force F, and along with this couple F into E, where F is equal to this 10 kilonewton. So once you are transferring, then there F 10 kilonewton will not be there. So then 10 kilonewton will be acting here. So this is 10 kilonewton, and this will be equal to F into E, where E is equal to 500 mm. We will be substituting all this required values to obtain first the primary shear load, then secondary shear load will be evaluated, then the maximum resultant load will be evaluated, and finally the tensile area, and hence the bolt will be selected. So here you can see the primary as well as secondary shear load at each of these bolt locations are shown. So first I will be here all the primary shear loads at F1A, F1B, the F1A, F2A, F3A and F4A will be equal to each other, and you can find, since we are already knowing the bolt at A is critically loaded or maximum resultant shear load is acting at A, you will be evaluating this F1AS, the total force acting divided by 4, since the 4 bolts are there, and that you can, for that you can use this equation. Once you are evaluating, you will be getting the primary shear load as 10 kilonewton by 4, that is 2.5 kilonewton or 2500 Newton. Next you will be evaluating the secondary shear load. For this you will be using this expression, and secondary shear load at each of these bolt locations are same, since RA is same as RB is same as RC is same as RD, and here we will be evaluating the distances of this RA or RB. So CG you are having here, so this distance if you are knowing, then you can find this RA or RB, all are same. So this distance will be equal to 200 by 200, and this distance will be equal to 150 by 2, that is 75. So this RA square or all of these values are same, and this one will be equal to square root of 100 square plus 50 square. So if you are evaluating, you will be getting this radial distance as 125 mm, which is same for all the positions, bolt locations. And also you can evaluate the theta from here. So if you are observing the theta at this position, then here actually in the finding resultant we will requiring the value of cos theta. So from this triangle itself you can evaluate cos theta as the adjacent side 100 divided by hypotenuse. Hypotenuse is actually the RA, that is 125, then this will be equated to equal to 0.8. So this is the value of cos theta. So now we have evaluated primary, the angle between primary and secondary. Now we have to evaluate the magnitude of secondary, that is F2A, which is equal to F2B or F3, F2A, F2B, F2C, and all values will be same. And now we will be finding this one. So this will be equal to F into E into RA divided by sigma RA square. Sigma RA square means RA square plus RB square plus RC square plus RD square. So if you are evaluating, finally you will be getting the F2A as F2A value you will be getting. Secondary is also same at all these locations, and that will be equal to 10 kilonewton you will be obtaining, or this is equal to 10,000 Newton. So now you are having the primary shear load and secondary shear load you are having. From this you will be evaluating the resultant shear load, and you are having the angle theta between this one. Theta you are having, so based on that cos theta also having. So if you are finding the resultant load at A, that will be equal to square root of F1A square plus F2A square plus 2F1A F2A cos theta A, and F1A is 2500 Newton, F2A is 10,000 Newton, and cos theta is 0.8. So if you are evaluating, you will be getting the maximum shear load at A and B are same, so that is equal to 12,093 Newton. So from this you will be evaluating the maximum shear stress, and maximum shear stress will be equal to shear load, resultant shear load by shear area, that is corresponding to the weakest section, that we will be taking as AT, and this should be equated, or this should be equated to the given property, that is toe allowable. So in this problem actually it is given the value of sigma yield, so this toe allowable should be equal to toe yield divided by factor of safety, and toe yield will be equal to half of sigma y, that is sigma y by 2 divided by factor of safety. It is mentioned to take a value of 2.5. So sigma y is given, so it is equal to 400 megapascal. I am substituting in as 400 divided by 2, then this will be having a unit of Newton per mm square, and divided by 2.5 is the factor of safety. Here this 12,000 is in Newton, so left side you are having force in Newton, and right side you are having the stress in Newton per mm square. Then if you are solving, you will be getting 18 units of mm square, and the value of AT you are getting once you are solving this one is AT, or the tensile area, is equal to 151.17 mm square. So based on this one, you will be selecting the bolt from the data book, for which you will be using table 9.8. So here the value of AT obtained is 151.17 mm square. So finally here you can see from this table 9.8 given in page number 141. So the value to be taken is the next higher value, that is corresponding to 157. So the final selected bolt will be of M16 with the pitch. So final answer will be, we will be selecting the bolt of M16 by 2. That means 16 mm major or nominal diameter with a pitch of 2 mm. So this is the final answer where this eccentric load is acting on this bolted joints. So thanks for watching. Hope you understood.